Welcome back to 6034 Fall 2020. This time I'm not going to be doing a recitation because we've already covered all the essential topics of 6034, at least the way it's taught in Fall 2020. What I'll be doing in this installment and in the following installments of 6034 videos is we're going to be doing review sessions of the topics that you've seen so far. And today's review session is one of four. It's going to cover the first three topics: search, games, which is adversarial search, and constraint satisfaction problems. And the way I'll be doing it is I'll be going through the quiz that was administered on these topics on this semester, and I'll be solving it in real time in the hopes that perhaps maybe the insights or the way I approach a problem or the way I think about the theory is helpful to you, and perhaps also in refreshing the material that, in this case, in review session number 1 was covered many weeks ago. Those were the first set of first 3 videos out of perhaps 10, I believe, so far, 11 with this one. So it's definitely been a while, and I think it would be a worthy refresher for including myself, which is why I'm solving it in real time. I will have the full disclosure, my notes on hand in case I need to reference something, but I've mostly checked, and I know that I know this material, and hopefully I can convey that to you in a concise and clean manner. So on with the PDF itself. Let's see, hopefully, yes, I believe that's legible. So first things first, it can be a quiz if it's not signed, and typically we ask for the students' emails, so this one is noneofyour@business.com, and the problems are in the order in which they were taught in the course and in the recitation videos. So those of you who have taken the quiz, you've already read this prompt. The context for anyone who's not registered for the class this semester is we typically write fun prompts for each problem. Because I'm focusing on the problems themselves, I'm not going to address the prompt. I'm just going to work on the problems and the quiz questions themselves. So feel free to, I'm going to take a second to pause on each of these prompts. Feel free to pause the video, read it at your own leisure, and then resume playing. So we're given this graph, and most of the questions that follow are going to be based on this graph. For example, in this one, which is a fairly simple question as a warm-up, what is the shortest path in terms of edge length between S and G? And as a reminder, edge length refers to these, essentially weights on each of the edges. And the other reminder is that these are heuristic values, and heuristics being the estimated distance from that node to the goal. It's a rule of thumb, it's not guaranteed, and if you are having a hard time remembering what heuristics are, I recommend you check out the earlier videos, of course. And important for this test is for you to know how to check for admissible and consistent heuristics. In this case, in this problem in particular, it doesn't really matter because we're just looking for shortest edge length. And so I'll just adopt a greedy approach in this case. I'll use a highlighter to trace more or less where my eyes are going. So this is the shortest path I've seen so far. This is 6 plus 4 is 10. This is 18, which is the shortest I've seen, and then I can either go down to E, which would make it 21, or straight to G, which would make it 20. So I believe that is the shortest path. And checking the solutions to make sure I haven't said anything egregious, that is in fact the solution. So it's S, A, C, D, and G. Okay, and what follows now is I'm going to conduct a depth first search on that graph in the hopes of finding goal node G. Regardless of the path, I just have to use depth first search. And I see that the graph is now out of view. So included in every test, of course, is a set of tear-off sheets in which you have copies of the multiple diagrams and graphs in the test for your own benefit. I'm going to project it here. And so I'll be referencing the graph on the screen as I work on on this depth first search problem. Okay, so the start node is S, and this is depth first search. So, well, so far it's not making any difference because I have to expand this level. And this is where depth first search kicks in, because technically if I'm thinking of the queue, which I talked about a lot in the search recitation, is then right now I have SA and SB in the queue. SA was added first just because it came alphabetically first. It's the leftmost child, and depth first search says always explore the leftmost child first. Or in other words, when you open a path, you add things to the front of the queue, not the back. So I have SA, and I'm going to expand that, and SA connects to C and only C. I add SAC to the front of the queue, which means now the queue is SAC and then SB. So I expand C again, and C has 3 possible paths it can take. I can take it back to B, I could go to D, or E. I'm writing them in alphabetical order from left to right. And so the next one to explore is B, the leftmost child. Let's see, B could go to D in this case, and only D. So we're not adding paths that would create a loop or a circle. And so D is leftmost child again. D is the first one, or the leftmost child. It breaks down into E and G, and this is where this is a good stopping point to reiterate that here in 6034 we consider that we found the goal node once the path with the goal node has been added to the queue, it's been taken off the queue, and I've tried to expand or explore what is after this path, and then I realize, oh, this actually is the goal, then I'm done. So what's happened here is I have both of these paths on the queue, and I'm not going to try to say all the letters in it because it's a mouthful, and I have this path on the queue, SB. So I'm going to pop this path off the queue, and it's going to be, and then I'm going to add SACBDEG to the queue, and the path after it is SACBDG. I said I wouldn't say it, but I couldn't help myself, and then SB. And so now I'm going to expand this path, as in I take it off the queue, and I'm going to expand it, and then I realize, oh shoot, this is the goal node, which means, I'll just keep it yellow. This is the path found by DFS in the 6034 implementation. 6034 Fall 2020, I should clarify. So our final path is S, A, C, B, D, E, and G. I haven't done the greatest job of keeping within the margins. Moving on, the classic, I won't say counter question, but the follow-up question to that is, okay, do exactly what you just did, but with breadth first search instead of depth first search. And the way I think about depth first search, yes, theoretically, or the theory behind it is you add paths to the back of the queue instead of the front, and that's what leads to the radically different behavior. The way I think about it is I have my S, and it's going to start the same. It first goes to A and B. Now, the way I think about it is this entire level, the next level, has to be expanded before I move on to the next one. So I have SA and SB in the queue, and I pop SA, I expand it, I have C, and I add SAC to the back of the queue, which means next in line is SB. I expand SB, and it yields 2 paths, SBC and SBD. And so those are added to the back of the queue, but then now you see the pattern where before moving to the next level, I filled out the entirety of this. I'm going to call this the second level, assuming this is level 0. Right, I've expanded the second level, now I'm going to move on to the next one. So next in line, I've expanded this entire level, which means I'm starting again with the leftmost child. I expand it out to I'm trying to read the graph. This is to B, D, or E. And then I expand SBC, and because I just expanded it, or I just expanded node B this time, or node C, I can't go in a loop, so it's not going to go back to B, but it can go to A this time, because that would not, SBCA is not a loop. SBCB then would have been a loop, and the same with the other C. SACB is not a loop, but SACA would be. So I start with A. The other path that is expanded is D. And then finally E. I'll try to make more space now when I expand D, which would be C, E, and G. So now all the paths are in the loop, or sorry, all these paths are in the queue, and the same as I explained previously, SBDG is in the queue. I haven't expanded it yet, which is why I haven't stopped, and now I'm going to go ahead and expand everything, or expand the next level. So B goes to D. D could go to B, E, or G. I'll try to cram everything. And then E could go to either D or G. Where could A go? Nowhere, so I'm not going to expand that one. Otherwise, I would be going in circles. Then D would go to E or G. E, same thing, D or G. Oh, I misspoke. The D would go to E or G, then E would go to D or G. Or perhaps I didn't misspeak. The letters are already having their overwhelming effect. C is A and E. E could go to C and G in this case. And now I go to finally expand G, and I realize, oh wait, G is in fact the goal node, which means my search terminates there. So my path is, whoops, S, B, D, G. Moving on, this is a conceptual question. I've talked about it already earlier as I was explaining how I think about DFS and BFS. But just to quickly summarize what it is, DFS adds, I'm catching up on my own notes. DFS adds new paths to the front of the queue. I'm just going to write front. And then BFS adds new paths to the back. And that's all there is to it. And now comes an example of optimal search. So now we're asked to perform branch and bound with extended set and no heuristic on the graph. And we're also asked to keep track of the queue, and I'll have to obviously keep track of the extended set. Let's see, the graph is still visible, but I believe I could zoom in a little bit because I was struggling to see it myself. I wish I had thought of it sooner. No ugly text. Okay, so there's the graph. So we expand first. The way I'll do it is I try to be as methodical as possible in these. I'm going to highlight S, meaning I've popped S off the queue. Then I would write number 1 right next to S because I'm extending S. And I have now expanded to A and to B. And typically I write in a separate color the path length so far. So I'm going to, I think I was using yellow in my recitation for path length. Yellow I don't think is very visible. At least I don't think so anymore. Actually it is visible, but I'll switch to orange in the spirit of keeping the original color coding I was using. So this is 6, and this path length for B is 15. Which means my queue now becomes, because reminder, branch and bound sorts the, this is no heuristic, right? Yeah. When it's no heuristic, branch and bound sorts the queue by path length. So paths with shorter path length are added are moved to the front of the queue, longer path lengths to the back. That's SB. Oh, I forgot to open my extended set. I just have S so far. Let me pop SA off the queue. That means I have to add this little evaluation here. I'm expanding A, which means I add A to the extended set. And now where does A go? Just to C. That means I have a total path length so far of 10. 6 plus 4, yeah. Okay, and then I go back to the drawing, not the drawing board, I go back to the queue, and it is now SAC, SB. I restart, pop that off the queue, I expand C, that's the 3, that means I add it to the extended set as well, and C could go to either B, D, or E, if I'm reading correctly, yep. B, D, or E, let me write down the path lengths. So this is getting a little bit long. 6 plus 4 is 10, that's 22 for B. For D, it's 18, and for E, it's 32. And so now we start getting some more interesting behavior, at least, or some more interesting action on the queue. Because now the shortest path is SB, which we had ignored so far, and then followed by SACD, then SACB, and then SACE. Okay. Let's pop SB. I evaluated number 4. There's B. And from here I get C and D. Just C and D because going back to S would be a loop. This is 27 and 26. Then to write everything out on the queue is going to start taking multiple lines at this point. Now the first candidate is SACD, followed by SACB, SBD, SBC, and then SACE. SACD is popped off the queue, which means D is number 5. D goes to either E or G. Or actually, either E or D or B, because B is not technically not a loop. Even though B is in the extended set, we're not expanding B. B or D. Did I say that? No. B, E, G. So I want to highlight just very briefly that I added B. This is an implementational detail. So in 6034 fall 2020, the extended set kicks in when, let's say, SACDB. Let's assume that's the next path that is going to be expanded. Then that's where the extended set, I'm going to check it and say, oh, B I've already expanded before, which means there's no point in expanding this, and there I've pruned it. In perhaps other implementations, one might not even write B explicitly, but I think it's important to highlight that in this implementation in the semester, it's important that B is still a possible path that can be explored, is considered a possible exploration point, because we're not checking the extended set applies mostly when we are going to expand a path. Okay, so it's BEG. And I'm missing, I got caught up in my explanation, I'm missing the path lengths. This should be 29, 21, and 20. Okay, so this is going to be the long queue. Thankfully, this is the last step, because 20 is the shortest path length that we have available to explore, which means SACDG is the next path that is going to be explored, followed by SACDE, SACB, SBD, SBC, SACDB. Shoot, I apologize, I neglected to add D to the extended set when I expanded it earlier. And now I lost track of where I was. SBC, SACDB, and SACE. And finally, I'm going to expand SACDG, which means two things. Yes, I've expanded G, which means I've found because this is optimal search, I've found my shortest path. But important as well, it means I add G to the extended set because it technically is a path that it is a node G that I've popped off the queue for exploration and I've tried to expand. That's an important detail for the follow-up question. List the nodes in the extended set in the order extended. So it's exactly what I have written above. And it's very, very important to have have G in the extended set. And then the path, let me just read it off. SACDG. And happy to confirm that this matches the shortest path that we found in question A1 at the very beginning of this quiz. Okay, so this is a conceptual question again. What is basically, or is branch and bound with extended set and no heuristic and informed search? And this is the catch, no heuristic. And at the beginning of the semester, when on the search recitation, I divided the search methods into three categories: blind, informed, and optimal. If I'm remembering it correctly, informed were the searches that rely on heuristics, to conduct their exploration, and they are informed because they have some rule of thumb that they are using to estimate, in the case of the heuristic that we use in 6034, the distance from that particular node that they are on to the goal. They are informed by that heuristic, but in reality, optimal searches use path length, and it's especially true with this one, with branch and bound with the extended set, because it's explicitly not using heuristic. So it is not an informed search. And it isn't because it does not use heuristics. Abbreviated H. Had it been branch and bound with extended set and heuristics, then one could argue, yes, this is an informed search, technically, just because it uses heuristics. I would still say it's an optimal search because it uses path length. Okay, so this next question, there are many ways to answer it. The original intent of this question was to get students thinking about what pruning means in the context of search. And a common go-to answer was pruning is what happens in alpha beta pruning, because the name is the same, so it's an easy association. And technically it's not wrong, which means if you answered that when you took this quiz, if you count yourself lucky, the technicality saved the day. But what we refer to was when you think of when you're conducting a search, before you start, the space could be immense. And when we talk about pruning is when you designate sections of the space that you think are either uninteresting or do not have the right answer. So you're essentially reducing the size of the possibilities, or the space of possibilities, down to a more manageable size. And one algorithm that does that very well is beam search. And I'll write it out explicitly, and this is where the confusion stems. Best first is the only one of the informed searches that sorts the agenda, or the queue. I forget to stick to queue sometimes. Beam is like BFS in that I was correct. BFS-like in that it adds paths to the back of the queue. But the detail that I missed was it's not that Beam sorts the queue and then only looks at the top W paths. It's that it expands the entire level, it sorts them by heuristic, and then it picks only the top W, or the best W, to add to the back of the queue. So that's a key implementational detail as well, but one that frequently, and as you've just witnessed, gets a lot of students and even us, the TAs, confused. So it's not that Beam search sorts the queue per se, it's that it adds to the back of the queue like BFS, but the way it chooses to add to the back of the queue, or which paths to add to the back of the queue, is by sorting by heuristic and picking the top W. So that's and then by picking the top W, you are pruning by choosing not to explore the other possible paths that didn't make the cut. So now that that's cleared up, and we've done heuristic, what did we just do? It was branch and bound with extended set, no heuristic. And now we're doing branch and bound with extended set and heuristic. In other words, we're doing A star. And the graph is repeated there, but I have it right next on the screen right next to this iPad display. And I say let's just dive in and not waste any more time. where are we? So this is question B1. Yep. I'm pulling up the notes as well to make sure that I don't have to make any more breaks in the video and, you know, make it as cohesive as possible. So let's, whoops, my notation. I'm going to pop S off the queue. Let me open the extended set. There's S, because it's already marked with a 1. And much as we saw before, there's A and B, which means the queue is populated with SA and SB. Okay. Now I have to, I skipped a step. Remember how I was using orange to denote path lengths? I'm going to do that once more. So SA has 6, and I'm going to use blue for heuristic, plus 14. If you've forgotten how to do this mixed path length plus heuristic, I recommend you go to the earlier recitation video as usual, as I actually did to verify the beam search, but the beam search details. So I partake in my own recommendations, but I'll briefly explain it as I go along. So we have a path length of 15 here, plus a heuristic value of 6. For a total of 21, yes. Which means SA is first in the queue and then SB. Number 3. I first have to pop A off the queue, or SA. So number 2, I add it to my extended set, and I expand. SA goes to C, as in earlier, and now I get the path length, or the running path length, by adding the previous path length of 6 to the new one, 4. So this is 10. But now I only consider the heuristic distance of C. So this is 10 plus 10 for exactly 20 again. And the reason is, when we're using heuristics, we only consider, because heuristics in the way we use them is an estimate of the distance from the current node to the goal, then once I am at C, I'm no longer interested in the estimate from A to the goal. I'm interested in the estimate from C to the goal, but path length is still relevant because I've traveled a particular distance to C. So that one is cumulative. Let's see, where was I? SAC, which would mean SAC is next on the queue because SB is 21, a total score of 21, path length plus heuristic. Moving on, I pop SAC off the queue. I added a little 3 here. C is on the extended set now. And I expand it out to B, D, and E. So the path length up to B is 22. The path length up to D is 18. And up to E, it's 32. 10 plus 22. Yep. Whoops. 32. And then to incorporate the heuristic estimates, the heuristic estimate at B is 6. At D, it is 2. And at C, it's 4. So I should have 28, 20, and 36, which I do. This is not the most legible 4 I've ever written. Yeah. And my new Q is SACD, SB, SACB, and SACE. I pop a SACD off the queue, which means D receives a little 4 and is added to the extended set. And now I expand D, which means it can go to either B or E or G. To add the path lengths, B should be 29. Let's see, is it 29? This is 10, 18, 29, yes. E is then 18 plus 3 is 21. And G, 18 plus 2 is 20. Now to add, excuse me, let me grab some water. Thank you. So to add the heuristics, G has a heuristic estimate of 0 because it is the goal. Distance from the goal to itself is 0. E has an estimate of 4, and B has an estimate of 6. So the new Q, thankfully, is going to be SACDG. There, just so that it's clear. SACDG, SB, SACDE, SACB, SACDB, SACE. And thankfully, this is the last one we pop off the queue, or the first one, the next one to pop off the queue. I try to expand G, which means G is added to the extended set, and I realize that G is in fact the goal node, so this is where we terminate. And the following questions are follow-up. The extended set, even though it's above, I'll just write it down one more time in order as SACDG. And the path is, because A star was so efficient in this case, SACDG. So it's exactly the variables that we have in the extended set. So for this last question, we are asked to find a heuristic estimate for B that would make the graph both admissible and consistent. And if, just as a general reminder, an admissible graph means that it never overestimates the distance from a particular node to the goal. So admissible, that the heuristic distance from some node X to the goal is less than or equal to the length of the shortest path from X to the goal. Consistent is a little, because the goal is implied, sometimes you'll see written heuristic of X, and in this case the goal is implied, but I like to be explicit about it, especially because of the following. Consistent, there should be a general reminder. If you don't remember this, please visit the recitation 1 video. the heuristic estimate from x to the goal minus the heuristic estimate from some other node y to the goal, absolute value, should be less than or equal to the length of the shortest path between x and y. And so that one is a stronger constraint, so much so that admissible in reality is a special case of consistent. So admissible is when y is the goal as well. So if you say y is equal to g, then h of y and g becomes 0, as I mentioned in the earlier case with a star, and then it becomes the other side of the inequality becomes the length of the shortest path from x to g. And because consistent is much more powerful, graphs that have consistent heuristic are also have admissible heuristics. So consistent implies admissible, but admissible does not necessarily imply consistent. Okay, so let me start with admissible because it's much easier. If it's admissible, the heuristic of b to g should be less than or equal to the shortest path to g, which is 4. So I have my first constraint, it must be less than or equal to 4. And now I'm going to start testing the neighbors and see how that for consistency. So the heuristic of, I'm going to, instead of write from b, heuristic bg, I'm just going to abbreviate it to b, or ag, I'm abbreviating it to just a, because the heuristic is always the estimate to the goal, it's implied, and it's just much less to write. So the absolute value of hb minus ha should be less than or equal to the shortest path from a to b. And that should give me the inequality 3 less than or equal to, well, this is, let me clarify, h of b minus what is heuristic of a, 7, is less than or equal to, what's the shortest path? 5. H of b minus h of s less than or equal to shortest path from b and s, and that's 2. This is h of b minus 6. There's a lot of inequality involved in this problem. I'm going to write them out explicitly, give you a few pointers, and encourage you to work it out on your own, because I would be all night working some, or not all night, but I would have to write quite a bit, and I would rather give that time and energy to the other two problems in this exam. HB minus HC. This is again 2, and this is HB minus the heuristic of B minus the heuristic of C, which is 3. And then there's actually one more, but that is from B to the goal, so that one was the admissible one. So I'll leave it there, and the way I can do this is I can rewrite the inequalities the following way. I'm rewriting them, so I'm going to change color to make it a little bit clearer. There's a lot of ink on the little square. Because it's an absolute value, I can write the inequality the following way. H of b minus -7, or minus 7, the absolute value, means it's also equal to, or because it's less than or equal to 5, it's greater than or equal to -5. The same down here. -2 less than or equal to h of b minus 6 in this case. Less than or equal to 2. Again, -2 less than or equal to h of b minus 3 less than or equal to 2. And I can play around with it with these inequalities, and eventually we would find that let me just go ahead and solve a little bit. It's less than or equal to 12 h of b greater than or equal to 2. Then it's also less than or equal to 8, greater than or equal to 4, less than or equal to 5, greater than or equal to 1. So these are the ones to look out for. I'll switch to yet another color. So 4 is the highest number that I found on the left, so I know h of b must be greater than or equal to 4, and I also know it must be less than or equal to 4, which means the heuristic from b to g is equal to 4. Switching gears now, we're going to talk about adversarial search, which in some ways is a little bit more straightforward. And so I'm just going to pause. Feel free to pause the video here for however long you need. Read the prompt at your leisure, and then I'll work on the problem accordingly. Okay, so hopefully you've read the prompt. Where the first problem is a warm-up. It's solve this minimax problem. Just no decorations, no frills, nor anything. Allow me to update this. We're actually not going to need it too much, but I'll keep it there for reference. This is for part A. So minimax, it's fairly straightforward. I'm at a min level, which means I choose the lowest of these two values. That's a 7. I choose a 5 here, then a 4. Here's a 9, and a 1. Then the max level above it chooses the highest of all the values. So I get a 7 here, and I get a 9, and then the min is going to choose the smallest of the two. So this is 7, and it's good practice to highlight the minimax path. That's what we call this. So it's the solution found by the adversarial search. Or not the solution, the path. So A1 was precisely to perform minimax search on the tree above. Let me delete this. A2 is just confirming that we reached the right answer, which was 7. And I'm trying to catch up to my notes. Yeah. And so which leaf node was chosen? The leaf nodes are the ones at the bottom. I denoted them in this problem with squares, G1, and then the minimax path, which is A, B, D, G1. Just double checking. So this is, to be strict, write the path from left to right, top to bottom. So A first, the root node first, and then the lower nodes to the afterward. Don't start with G1, just standard convention. Okay. So now comes the big one. Feel free to pause and read the prompt. I'm just going to go straight ahead into this problem. And the first thing to note is the max and the min order has been switched around just to keep it interesting and on your toes. So it wouldn't yield the same minimax or the same value as in the previous problem. And we're asked to perform minimax first on this tree, and then we're asked a series of questions based on that. So the first thing to do is to initialize the alpha and beta variables. Here beta is, because beta wants to minimize, beta starts at infinity. Because alpha wants to maximize, it starts at negative infinity. And I go this direction to the leftmost child. So alpha is equal to negative infinity, beta is equal to infinity. And I go further down. Beta is equal to infinity, alpha still equal to negative infinity. And then I perform a static evaluation here. I see that it has a 7, which means alpha is greater than or equal to 7. And then I perform another static evaluation on 8. So that makes alpha greater than or equal to 8. Or better said, in this case, alpha is equal to 8. It was greater than or equal to 7 because we hadn't explored all the tree or all the leaf nodes. Once we've explored all the leaf nodes, we know alpha is equal to 8, the highest value found. And so this goes back up, meaning that beta in this case, because this is a minimizer level, beta is less than or equal to 8. And now we go back down. Notice that alpha at the top level is still negative infinity, which means that's what we see at the bottom. Oops. Now beta is less than or equal to 8, but alpha is still equal to negative infinity. I evaluate the 10. Which means alpha is greater than or equal to 10. And this is where red flags and alarm bells need to go off, because alpha is greater than or equal to beta at the moment, which means we've triggered the pruning condition. So we're not even going to bother checking the next leaf node G4, because we know the min level at the top level of this one level above, sorry, is never going to pick node E. So node E is not going to realize its full value because we're not going to evaluate all the leaf nodes, because B would never pick it anyway. So we are skipping over to F. And we go over to F. B is less than or equal to 8 still. Alpha is still equal to negative infinity. Then I evaluate F. It's the only leaf node, so I'm just going to go straight to alpha is equal to 4. And that makes, beta equal to 4. And that means at the top level, alpha is greater than or equal to 4. let's go to the next subtree, the right subtree. Alpha is greater than or equal to 4. It's inherited from the root node. B is equal to infinity. And then this again, B is equal to infinity. Alpha is greater than or equal to 4. And then it sees 9. So alpha is equal to 9. I go up. Beta is, oops, not equal, less than or equal to 9. Next level. The alpha at the min level is still greater than or equal to 4, which means alpha is greater than or equal to 4. Oops. I should have written beta first. Beta is less than or equal to 9. Alpha is greater than or equal to 4. I evaluate the 6. Alpha is greater than or equal to 6. And I evaluate the 3. The 1 at G8, the 3. And it's finalized that alpha is equal to 6. That is handed back up. And that also means that beta is equal to 6 at the top level. And that in turn is handed up once more. And then alpha takes a final value of 6. Now we're asked which leaf nodes were pruned. That was G4. And which decision nodes were pruned, and that would be E, because we did not evaluate all the leaf nodes of E, meaning that the final value of E was never realized by the algorithm. Moving on, in this question, we're asked to reconfigure the tree in one of two ways. So the first question asks to reconfigure the tree. This is why I had I still kept the tear-off sheet next to me. There you go. So we're asked to reconfigure the tree first in a way in which no leaf nodes would be pruned. And if I'm going to quickly scroll back, if we look at this, one very easy way of making no leaf nodes be pruned would have been, to flip around these two leaf nodes, because the prune condition happened because alpha became greater than or equal to 10, and the leaf node after it was skipped. But had alpha been greater than or equal to 5, that was still less than or equal to 8, which was beta's value at that time. So we would have proceeded to evaluate 10, and once 10 was evaluated, yes, the prune condition would have been triggered. So technically it would have been a prune, but 10 or G3 is the last leaf node of E. So technically it would have been a meaningless prune. So it can be argued that that was one where no prunes happened. So that's the first answer that I'm going to give. It's going to be A, B, C, D, E, F, this is G, and H. And then the leaf nodes would be G1 in this order. G2, G4, G3, G5, G6, G7, G8, and G9. That's one very ugly tree. Okay, so I'm looking through my notes because there are actually multiple ways of solving this. So that was the more simplistic way of solving it. A different way of solving it would have been, and this was actually the intention of the question, in the ordering of nodes, in the ideal ordering of nodes, the best nodes, so if it's a min level, the nodes with the lowest value, or if it's a maximizer level, the nodes with the highest value are ordered toward the left and are ordered in either increasing or decreasing from left to right, so from best to worst. That's the optimal ordering, and that's actually the concept that was being tested here. So the worst case scenario ordering of this question would have been, or of the leaf nodes, would have been the following. So it would have been G3, G4, followed by G1, G2, G5, G6, G7, G8, G9. And the reason this one worked in particular is if you perform minimax on this, you'll notice that on this minimizer level, the highest values are toward the left, and the left and the lowest values are toward the right for both B and C, which is why this caused no prunings. And this also translates to the lowest value being on the left in the case of A at the maximizer level. So B has a lower value. When you evaluate minimax on the B subtree, it has a lower value than the minimax on the C subtree. So from the perspective of A, that's also a suboptimal ordering. But there was actually a... So this is the next question. I thought that I had more space. There's yet another alternate solution to this, and it is the following. I'm going to eliminate the hacky one because it's just a simple reordering of two leaf nodes, just to present the third alternate solution. I ended up writing the leaf node values. I'll write the leaf node names below them. This is G6, G7, G8, G9, G4, G3, G1, G2, and G5. So this is an interesting case, and I won't go too deep into it. And the reason I want is I encourage you to perform minimax on this solution and think deeply about why this doesn't work and why it seems to defy the principle that we discussed earlier. Okay, so moving on. This is one, now we're looking at trees where there's a maximum amount of pruning happening. So we're doing the reverse of the previous question. We're aiming for ordering the leaf nodes and the higher nodes, the subtrees themselves, in ways that would cause more pruning, so more efficient alpha beta. The alpha beta algorithm would run faster. And there's one relatively general solution of the following form. I'm just going to leave the leaf node values as they are, because those are what determine whether something is pruned more than anything. F, D, and E. 4, 7, and 8, 10, and 5. So there are multiple different leaf orderings. This is just one I chose for this particular question. In reality, two things needed to happen in order for the number of prunings to be maximized in this problem. The first one was that C and B were flipped, because C has a higher value with respect to, so C has a value of 9, if you recall from the minimax, or has a value of 6, sorry, and B has a value of 4 from when we perform minimax. So having C on the left is ideal with respect to A, because the highest value is on the left for the maximizer. But then the other point is that H and G can they can be in any order in reality, because if to put it this way, if G had more children than just G6, then there would be more pruning. But because G6 is the only child of G, then it doesn't matter whether H or G are first, whether H or G is first. But in reality, the ideal setup is that H comes before G, and in the B subtree, the most important thing is that F is the leftmost subtree. So this is actually crucial, because F being first means the minimizer sees the lowest value in the entire subtree and then proceeds to prune 8 and 5 later. Okay, so I'm back, and let's jump right into problem 3. I trust that you've read the prompt and that you've had time to read the constraints. I'm just going to go straight ahead into problem A1. So this you haven't seen. I'll leave this up for a second. Feel free to pause the video, digest the information. I'm going to go ahead and update my... There we go. So this should be all the information you'll need. And as promised, straight to problem A1. So this is actually not a difficult question, but there's some amount of strong conceptual understanding that needs to happen here. So it's I'm going to write a common mistake, and then I'll backtrack into the correct solution. So 4, 5, and then it says that Balto must go on a fast route, so 1, 3, and Charlie and Balto's routes must be adjacent, so Charlie must be either 1 or 2 or 3 or 4, because those are the only possible values that would be adjacent to B. And then D, it cannot be adjacent, which means it can't be 5, it can't be 4, and perhaps it can be 3, perhaps not, so maybe it's 3. So it could be 1, 2, or 3. And then 2 or 4 for the last variable. But in reality, the mistake happens here and here, where the first two sets of constraints, these two, and this set of constraints, those are hard constraints. The dogs actually cannot walk on those paths as described by the prompt, but C and D are flexible constraints. So those are applied, those are, the way I think about them, they are after the fact constraints. So the way, not if you don't like the after the fact terminology, the other way I think about them, I like to think of these in multiple ways, is the C and D both depend on A and B. As in, the values that I have here depend on the values that I have here, which means I've reduced the domain of C and D by taking into account those constraints, whereas these don't depend on anything. Those are part of the problem itself. So 4 and 5, 1 and 3, 2 and 4 are correct. They're, as I mentioned, they're part of the problem, but 1, 2, 3, but what's the name of the dog was C, Charlie, theoretically could go on any path, it just can't be adjacent to B. So that's a constraint that I can't apply because it depends on the assignment of the value of another variable. And then the same with Douglas, 1, 2, 3, 4, and 5. Because it depends on the assignment of A, and that's not a hard constraint. So this is the original domain of each of those 5 variables. I recommend you, if this seems a little bit iffy, I recommend you revisit the constraint satisfaction problems recitation, and you know, and perhaps skim through it just as a refresher. Okay, so now we're asked to perform depth first search with forward checking and no backpropagation. Okay, so I'll just go ahead and write the domain of A, the domain of B, which I said was 1 and 3, domain of C, which is 1, 2, 3, 4, 5, the domain of D is also 1, 2, 3, 4, 5, and then E is 2 and 4. I have the graph on display on the left, so I'm just going to jump straight into it. I have a 4. I perform my forward checking, which means if I take all the constraints into account, Douglas must not be adjacent to Ada, meaning it cannot be 5. Ada's taking 4, it definitely can't be 4, it can't be 3, and no two dogs can take the same route, which means Charlie can't take 4, and who's Ellie? Ellie can't take 4 either. Okay, so moving on. Balto goes on route number 1, which means that Charlie can no longer go on route 3, nor can he go on route 1. Doug can't go on route 1, which means Doug can only go on route 2. Charlie goes on route 2. Doug can't go on route 2, and neither can Ellie, which means we have 2 empty domains. So we have to backtrack. I'm going to erase some of these markings according to how much we backtrack. We're backtracking up to Balto, and when I did, Douglas lost 1 from the domain, and I believe it lost 3 from the domain and 2. There we go. I believe this is a backtrack. Then I have 3. I'm going to color what I had previously, 1 and 2. So I'm taking 3 because it's sorry. I'm taking 3. I've backtracked from 1 because Balto's taking 3 and Charlie must be adjacent. Charlie can no longer be 1. And what else? Do I eliminate? No, I don't yet eliminate anything from Doug's domain except 3. And now I assign a 2 again to Charlie, which means this can't be 2, Doug can't be 2, and Ellie can't be 2. Ellie has an empty domain, so I actually backtrack before making this assignment. So that making that assignment would be incorrect because I have an empty domain here, and that means I have to backtrack on the spot. So the moment I had that empty domain, I had to throw everything out the window, backtrack. Let me color it in red. And I have to undo these eliminated constraints because I'm moving the root node of the tree. So this moves here, and I have to redo the constraints. So Charlie can't be 5 anymore. Doug can't be 5 according to its constraint. With not being adjacent, it can't be 4 either, and this doesn't seem to affect anyone else. Depth first search, B has 1 open, so we assign it a 1. Charlie can't be 1. It must be adjacent, so it can only either be 2 or 3, can't be 4. Doug can't be 1. This doesn't affect Ellie. So I assign 2, which means Doug can't be 2, neither can Ellie. Doug receives is assigned a 3, and then Ellie's assigned a 4. And this is the final assignment with essentially with the possible domains. So note that this 3 was open. It was never actually eliminated. So that's important to note, but all the others were eliminated by then. So another way of visualizing this answer would have been, I'm going to erase everything to rewrite it in a cleaner way. Would have been this. So these circles indicate that it was assigned at one time. So 2 was assigned twice, if you remember, and we backtracked at this point. And we went back up, and Balto could have been a 1 or a 3, but it had a 1. Charlie could have been a 2, 3, and then finally a 4. So actually, so I remember I left a 3 here for in the case of Charlie. That was a slight oversight. It should have been eliminated by forward checking. Because when I assigned 1 to Balto, 3 is not adjacent to 1, so that 1 should have been that 3 should have been eliminated as well, and this 3 in the domain of Balto should be the only 3 that was basically left unassigned, or that was the extra value in the domain. Okay, so the next question asks, what would be a way of assigning the variables that would have not required backtracking? And there are actually many solutions to this. There are, I'm going to count them really quick because I can see them. There are 12 ways of ordering the variables such that there are no backtracking, but I'm just going to give you 2 of them. The way I find some of these is I think which are the most strict constraints. In the case of the problem above, we saw that Ellie had an empty domain twice in a row. So I would think Ellie probably should be assigned first, and or one of the first and being assigned, and it's no coincidence that one of the possible orderings is E, D, B, C, A. And then the other to think about is the other variables with shorter domains. So B, for example, B's domain does not affect Ellie's domain, but B's domain does affect C's domain. But in reality, if we assign B first, we get a 1. If we assign C right next to it, it's 2, and that leaves Ellie with 4. So that's a possible ordering, or that's one that seems correct initially. And if we explore it further, B, C, E, A, D happens to be a proper ordering, and it's no coincidence that B, C, E, D, A is also an ordering, B, C, D, E, A, and so on and so forth. So it's a good practice exercise for you to find more orderings and figure out how can you think about this problem in such a way that you find the orderings relatively quickly. This is in case you wanted to do the same problem twice, if we were doing it on ink, that is. And now we get to domain reduction. We're given some more story. I should have paused briefly. Feel free to pause the video, read the prompt. There is where you can read the beginning of the prompt. Apologies. And there you can pause again and read the prompt one more time. Allow me to pull it up right here. And I'm going to scroll down and just cut out some of the context because I want to be able to see the constraint graph. And now I have all the information at my disposal. So the first thing to do here is I'm going to start a prop queue. And because this is domain reduction, all the variables start on the prop queue in alphabetical order. So A is dequeued according to the instructions, and I need to look. Give me 1 second. I want to catch up to my own notes. Okay. I look at A's domain, and I see it's 1, 2, 3. I look at the constraints on the other window, and I see that there's no, because A's domain is relatively flexible, it can either be 1 or 2 or 3. There's no there is no value in the other variables that when assigned would conflict with every single value in the domain of A. That's where we would eliminate something from the domain of another variable. So we don't eliminate anything. We dequeue B, and we perform the same check. Is there a value in the domain of one of the other variables that when assigned would conflict with B being 1 or 2 or 3, as in would conflict with either of those 3 assignments, and there isn't one? C is the same story, and J, unsurprisingly, because they have domains of 3, so they can be flexible. Now when we get to K, K has a domain of 1, which means let's look at A, for example. Which assignment of A, or which value in the domain of A conflicts with every single value in the domain of K? Well, that would be 1, which means A cannot be 1, according to the constraint graph that I have on the left side of the screen, and J also cannot be 1, because it also conflicts with every single value in the domain of K, which just happens to be 1. And because we've changed the domain of A and J, they go back onto the prop Q. And I'm going to start eliminating values from their domains here. Okay. On to the next one. That's L. And L has a similar story. Because it only has one value in its domain, when J is equal to 3, that conflicts with every single value in the domain of L. So J cannot be 3. And according to the constraint graph, C cannot be 1 nor 2. Because L and C must be paired together. And because L only has one value in the domain, 1 and 2 both conflict because they break the constraint that C and L must be together. Let me update the graph here. And that means that I'm at L, I modified J, and I modified C, but J is already on the prop queue because of K, which means that C goes on the prop queue, just C. Now I take A off the prop queue. A has 2 possible values, so it's still fairly flexible, as in no values of the other variables conflict with both 2 and with A being both 2 or 3. Or should I say with both A being 2 or A being 3. Same story with J. It still has 2 values in its domain. And now it's C. C has become a singleton, so this will likely eliminate values from the domains of its neighbors. And unsurprisingly, it eliminates 3 from A, because now 3 now conflicts with the entirety of C's domain, and it eliminates 3 from B, which means A and B are added back to the prop queue. I take A off the prop queue. Now B cannot be equal to 2 because A, the only value Oh shoot, I forgot to update. So with C, A cannot be 3 and B cannot be 3. There. And J could not be 3 according to L. C cannot be 1 or 2. Yep. Okay, now I'm up to date. So at row number 10, B cannot be 2 according to A. So B is now a singleton, but I don't add it to the prop queue again. I don't add B back to the prop queue because it's already on the prop queue. And I pop B off the prop queue. All the other values are singletons, or all the other variables are singletons or have singleton domains, and they don't conflict according to the assignments. So B is none, and we are done with domain reduction. So this has been, as promised. I know I mentioned my notes a few times. I wasn't relying on my notes before writing down the answers. I was trying to solve the quiz in real time, and as you may have expected, that brought with it its own set of difficulties. I sometimes confuse, not confuse the concepts, but similar terms get mixed up, and I'll try to edit those. I've tried to edit those as much as possible such that you have a seamless experience, but the main purpose being that you've been exposed to the earlier content of the course one more time, and that this has helped you refresh your memory on what you were seeing, what the steps were to solve these problems, and what the general algorithms and the general algorithmic thinking was to move through these mechanically and solve them in a straightforward way. So there are more of these to come with the remaining topics, but for now I'll see you on the next one. I hope that this was useful to you in reviewing. As always, refer to the earlier videos if you have any further questions, doubts, concerns, or need a deeper refresh of the material.